let us see if we can apply what we have learned to find out the general expression for acceleration in a frame that is both translating as well as rotating. So once again, let us consider two frames. One frame is stationary with respect to the ground. Let us call that the sigma frame, and these are its axes, x, y, z axis. And let us have another frame that is both translating as well as rotating with respect to the first frame. Let its axis be called x primed, y primed and z primed, and it is both translating as well as rotating about its own z axis with an angular velocity of omega, and it is translating as seen from the unprimed frame of reference. So if I consider a point here, then the position vector of that point as seen from the sigma frame, so this is my sigma frame, whereas this is my sigma primed frame. So the position vector of that point is, let us say, r vector, and if I join these 2 points, then this will represent the position vector of the point as seen from the primed frame of reference, and let us call that the r primed vector. Obviously, in this case, the two frames of reference do not agree as to what the position vector of a certain point is, and let us call this the a vector. All these vectors, if the point is moving through space in some arbitrary way, all these vectors are functions of time. Even a is a function of time, because the sigma primed frame is moving is translating with respect to the sigma frame. So from triangle law here we can write that r vector equals to r primed vector plus a vector. So if I now differentiate both sides with respect to time as seen from the sigma frame, I can say that dr over dt as seen from the sigma frame equals to dr primed over dt as seen from the sigma frame plus dA over dt as seen from the sigma frame. dA over dt as seen from the sigma frame is the velocity of the sigma primed frame as seen from the sigma frame. Now let us consider a vector which is stationary as seen from the primed frame of reference. The position vector of that particular point is r primed, let us say, this r primed being different from this r primed. Forgive my notation. Let us consider this vector which is stationary in the primed frame of reference. So what will we say about the velocity of this point as seen from the unprimed frame of reference? Now, because this vector is stationary in the primed frame of reference, as seen from the unprimed frame of reference, it will have two velocities. One is the velocity of the frame itself as seen from the unprimed frame of reference, and the other is because of the rotation of the frame itself, of the sigma primed frame itself. So because of the rotation of the sigma primed frame is rotating with angular velocity omega, where omega lies along the z axis. The r primed vector itself rotates like so. So as seen from the sigma frame, the velocity of this point is the sum or the vector sum of the velocities of the primed frame itself and the velocity this point possesses because of the rotation of the primed frame itself. So if the position vector of this point as seen from the unprimed frame of reference, say, is r, then we can say that dr over dt as seen from the sigma frame of reference is dA over dt as seen from the sigma frame of reference plus omega vector cross r primed vector. Both frames of reference agree as to what the omega vector is. They also agree on the description of omega, because omega lies along the z-axis, and z prime and the z-axis, they are oriented along the same direction. So in place of this we can substitute this. If we do that, we shall get dr primed over dt sigma plus dA over dt sigma equals to dA over dt sigma plus omega cross r primed. I can cancel out these two terms, from where I can say that dr over dt sigma equals to omega cross r primed. So we get back to this formula, which says that if r prime is a vector that is stationary in the primed frame of reference, its time derivative with respect to the unprimed frame of reference is given by this formula. Now let me write out the expansion of r and r prime and differentiate this equation with respect to time as seen from the unprimed frame of reference. Therefore, I can say that dr over dt as seen from sigma equals to dr primed over dt as seen from sigma, which is d dt of x primed I cap primed plus y primed j cap primed plus z primed k cap primed. This differentiation being done from the sigma frame of reference plus dA over dt as seen from the sigma frame of reference. So this gives us dr over dt as seen from the sigma frame of reference is just the velocity of the particle as seen from the sigma frame of reference. This becomes x primed d I cap primed over dt as seen in sigma plus y primed d j cap primed over dt as seen in sigma plus z primed d k cap primed over dt sigma, plus we have more terms, and they are I cap primed d x primed over dt sigma plus j cap primed dy primed over dt sigma plus k cap primed dz primed over dt sigma, and we have this term, so that is dA vector over dt as seen in sigma. Now here we are only differentiating scalar functions of time, so it does not matter from which frame we differentiate them. So we can as well write sigma prime in place of sigma, and this whole thing becomes dr prime over dt as seen in the sigma primed frame of reference, because in the sigma primed frame of reference these vectors are constant vectors. So I get, let me just jump one step and say that this will be equal to omega cross I cap primed from this equation, because I cap, j cap, k cap, they are all constant vectors as seen from the primed frame of reference, and this formula holds for an r primed vector which is constant in the primed frame of reference. We can apply this formula for these derivatives, and we can say that this is x primed times omega cross I cap primed y primed omega cross j cap primed z primed omega cross k cap primed. So we get omega cross r primed. This becomes the derivative of r primed as seen from the primed frame of reference. So this is just dr primed over dt as seen in sigma primed, and the final term is plus dA over dt as seen in sigma. So we have a formula V equals to V primed plus omega cross r primed plus dr primed over dt sigma primed. I'm sorry, I had made a mistake in this step. In copying from here to here, I had mistakenly written r primed vector. D dt of r primed vector from with respect to sigma primed vector is what I had written, but it actually will be just this term, dA vector over dt as seen from sigma. So the only difference between this equation and this equation was for a vector which is stationary as seen from the primed frame of reference. Therefore, as seen from the unprimed frame of reference, it only was rotating with as seen from the unprimed frame of reference, as well as translating because of the translation of the primed frame itself. In this case, if this particle is itself moving with respect to the primed frame of reference, we get this extra term, which is the velocity of this point with respect to the primed frame itself. Therefore, the net velocity as seen from the unprimed frame is the velocity with respect to the primed frame plus the rotational velocity which exists because of the rotation of the primed frame itself, and this velocity, which is the velocity of the primed frame as seen from the unprimed frame. Now, to get an expression for acceleration, let us differentiate this equation with respect to time as seen from the sigma frame of reference. So this becomes dV over dt as seen from sigma equals to dV primed over dt as seen from sigma plus differentiation of this term as seen from sigma, which will be d omega over dt cross r primed as seen from the sigma frame of reference is just r primed, and d omega over dt, about this term both frames agree. Therefore, we don't have to specify with respect to which frame this differentiation is being done, plus omega cross dr primed over dt plus double derivative of this term, which is d squared a over dt squared as seen from sigma frame of reference. So this is just a vector equals to, we'll have to do this differentiation. So let me just write it out, d dt of I cap prime vx prime plus j cap prime vy prime plus k cap prime vz prime. Let me just for this step I'm not writing these terms out, just imagine that they are there. So if I just do this differentiation, and this differentiation is being done from the sigma frame of reference, so I get I cap primed d dt of Vx primed as seen from the sigma frame of reference plus j cap primed d dt of Vy primed as seen from the sigma frame of reference plus k cap primed d dt of Vz primed as seen from the sigma frame of reference plus yet more terms Vx primed d dt of I cap primed as seen from sigma plus Vy primed d dt of j cap primed as seen from sigma plus Vz primed d dt of k cap primed as seen from sigma. So here again we are differentiating only scalar functions of time. So I can as well differentiate them with respect to the sigma primed frame of reference, and these components therefore become the components of acceleration of the particle as seen from the primed frame of reference. Therefore this whole vector becomes the acceleration of the vector acceleration of the particle as seen from the primed frame of reference. Therefore, this whole thing is just a vector primed or a primed vector, and for d dt of I cap primed, I can just write omega cross I cap primed. Similarly for these, similarly for this, I can write omega cross j cap primed. For this, I can write omega cross k cap primed. Therefore, I can say that a vector is equals to a primed vector plus, this is just Vx primed times omega cross I cap primed, Vy primed, omega cross j cap primed. So let me write those down. Vx primed times omega cross I cap primed plus Vy primed, omega cross j cap primed plus Vz primed, omega cross k cap primed. There are yet more terms. I'm just avoiding writing them for the moment. So this is just a vector equals to a primed vector plus, this is obviously omega cross v primed vector. And let me now write out the remaining terms. I have a d omega over dt cross r primed vector. So I have a d omega vector over dt cross r primed vector plus, I have a omega cross dr primed over dt. Dr primed over dt having been done from the sigma frame of reference, because I was differentiating this whole equation with respect to the sigma frame of reference. Now dr primed over dt as seen from the sigma frame of reference, we can figure that out too, but I think we had already done it here. We had differentiated this whole equation with respect to the sigma frame of reference, and the differentiation of this part, only this part, from there I think we had gotten, this was, I think this was the omega cross r primed vector, and the remaining term was the derivative of r primed vector as seen from the primed frame of reference. So differentiating this, that is differentiating r primed with respect to time as seen from the sigma frame of reference, we had gotten omega cross r primed plus dr primed over dt as seen from the sigma primed frame of reference. This was our omega cross r primed, and this was the derivative of the r primed vector with respect to time as seen from the sigma primed frame of reference. So let me just substitute these two terms for this. So what do I get? I get a omega cross, I have omega cross this, and this is just this part, which is omega cross r primed, plus this is just actually v primed. So omega cross r primed plus v primed. Did I have more terms? Yeah, I have this term also, which was d squared a vector over dt squared as seen from the sigma frame of reference. So finally we get a vector equals to a primed vector plus, I have a omega cross v prime from here, another omega cross v prime from here, so I have a 2 omega cross v primed. I have a omega cross r primed. This is my centrifugal acceleration term, this is my Coriolis acceleration term. I have, I think, two more terms, d omega by dt cross r primed plus d squared a over dt squared as done from the sigma frame of reference. I think this is our final expression written out in all its glory. A being the acceleration of a particle as seen from the unprimed frame of reference, and A prime is the acceleration of the same particle as seen from the primed frame of reference. We have this extra term. This is the pseudo force that arises from the translational accelerated motion of the primed frame itself, and the rest of the terms are actually common. Only in the previous derivation we had got r here as far as I can remember, but that is only natural. In this case, my position vector r prime is rotating around the z primed axis, so it makes sense to have r primed in my centrifugal acceleration term. The previous derivation, we had got an equation like this, which we had generalized to any vector in place of r. Let us see if we can get a similar expression for this particular situation, for this particular derivation, and for that we need the expression for velocity which we had derived, the general expression for velocity, which is v vector equals to v primed vector plus omega cross r prime plus dA vector over dt as seen from the sigma frame of reference. Yeah. So v vector is just dr vector over dt as seen from the sigma frame of reference. V primed is dr primed over dt as seen from the sigma primed frame of reference plus omega cross r primed plus dA vector over dt as seen from sigma frame of reference. Now r vector in this situation is just r primed vector plus a vector. Remember that r primed, a, they are all functions of time. So in place of r, if I substitute this, then I can say that dr primed over dt as seen from the sigma frame of reference plus dA over dt as seen from the sigma frame of reference equals to dr primed over dt as seen from sigma primed plus omega cross r primed plus dA over dt as seen from sigma frame of reference. These two terms will obviously cancel out. I'm sorry, there's an r primed here. So we get dr primed over dt as seen from sigma frame of reference equals to dr primed over dt as seen from sigma primed frame of reference plus omega cross r primed. Here we get the same equation back, and now we can generalize this for any vector. In place of r primed, we can place any vector. Note that in this case our r primed, say, is this vector, but this is a specific vector. It does not matter from which frame I describe r prime vector. I can as well describe this vector, the r primed vector, from the unprimed frame of reference. So this equation actually holds for any vector. Here r primed vector means a specific vector, but the description of r primed is in the primed frame of reference, but we can describe this very vector from the unprimed frame of reference. Therefore, this equation will be true even if the description of r primed is in the unprimed frame of reference. And then we can generalize this equation for any vector in place of r primed. If you are not convinced, you can prove that this equation is true for any vector. Let's say that I have a vector A and its representation in the primed frame of reference. Let's say it is ax primed, I cap primed plus ay primed, j cap primed plus az primed, k cap primed. So what happens if I differentiate this equation from the from the unprimed frame of reference, that is from the sigma frame of reference? If I do that, I get dA primed over dt as seen from sigma, that is equals to excuse me, ax primed di cap primed over dt as seen from sigma plus ay primed dj cap primed over dt as seen from sigma plus az primed dk cap primed over dt as seen from sigma plus I cap primed dax primed over dt as seen from sigma plus j cap primed day primed over dt as seen from sigma plus k cap primed daz primed over dt as seen from sigma. And here, because we are differentiating again terms which are scalar quantities, although they are functions of time, they are scalar functions of time. It does not matter from which frame I differentiate them, therefore I can differentiate them from the primed frame of reference. So the first term becomes ax primed omega cross I cap primed. Similarly, the second term is ay primed omega cross j cap primed. The third term is az primed omega cross k cap primed. And what do these three terms combine to give us? They give us the differentiation of the a primed vector with respect to time as seen from the sigma primed frame of reference, because in the sigma primed frame of reference, I cap primed, j cap primed, k cap primed, they are all constants. So this gives us omega cross a vector primed. These three terms, they combine to give us this, plus dA primed over dt as seen from sigma prime. So for any vector A, I can write, for any vector A primed, I can write dA primed over dt as seen from sigma equals to dA primed over dt as seen from sigma primed plus omega cross A primed. And because A vector and A primed vector are equal, fundamentally I am talking about the same vector, but now the representation of A primed vector can be written in terms of the unprimed frame. Therefore I can easily substitute A vector in place of A primed vector, because fundamentally I am talking about the same vector, only my representation has changed. So this just becomes dA over dt as seen from sigma frame of reference equals to dA over dt as seen from sigma primed frame of reference plus omega cross A. So here is my equation, which says that this is not only true, this equation is not only true for position vectors, they are true for any vector. Now let us see that if we can derive the expression of acceleration that we got for a particle that is moving in a frame, the frame itself having translational motion and rotational motion with respect to the ground frame. Let me see if we can derive that formula for acceleration using this equation. So we now have dA over dt sigma equals to dA over dt as seen from sigma primed plus omega cross A. Yeah. Now let me substitute, let me substitute V prime in place of the A vectors. If I do that, I can just as well substitute V. My final result will be the same, although my steps will be slightly different. But For now, let me just substitute v prime in place of a vector. So I get this. Notice that this is an equation we had found previously. I'll have to search for it, I think. We did find it before. Let's see. Yeah, we had differentiated v prime as seen from the sigma frame, and we had ended up with the first two terms. The first term a prime is just this, and omega cross v prime is omega cross v prime. So anyway, now we also have the expression for velocity, which is v vector equals to v primed vector plus omega vector cross r primed vector plus dA vector over dt as seen from the sigma frame of reference. Let me just check this. I don't want to make a mistake. This is a lot of work. Yeah, we are right. So moving ahead. So now, in place of v prime, let me substitute v minus this term minus this term. If I had used v in place of a, then I would have had to substitute v in terms of v prime in this term. In any case, here I am substituting v in terms of v prime from here. So in place of v prime, I will simply be writing this minus this minus this. So what is dv by dt as seen from sigma frame of reference? That's just a minus the derivative of this term with respect to the sigma frame of reference. That just becomes d omega over dt with respect to the sigma frame, but I don't have to specify that, cross r primed in the sigma frame is just r primed minus omega cross dr primed over dt as seen from the sigma frame minus d squared a over dt squared as seen from the sigma frame equals to, this term is just a primed plus omega cross v primed. So this now gives us a vector minus d omega over dt cross r primed minus omega cross, now what is dr primed over dt? We have just seen that dr primed over dt, where is that? We have just seen that dr primed over dt is given by this equation at the bottom. So dr primed over dt as done in the sigma frame is just dr primed over dt as seen in the sigma primed frame, which is just v primed plus omega cross r primed. So that's this term minus d squared a over dt squared sigma equals to a primed vector plus omega cross v primed. Let me keep only a on the left hand side and bring the rest of the terms to the other side. This is minus omega cross v primed. I have a plus omega cross v primed here. So on the right hand side I get 2 omega cross v primed. This is primed. I have a minus omega cross r primed. Let me take that to that side, to the right hand side. So I get omega cross r primed with a plus sign out in front. I have a plus d omega over dt cross r primed. I also have a primed here, and if I bring this term to that side, this is just d squared a over dt squared as seen from the sigma frame of reference. And here is our equation written out in full glory. So before we had found this. Obviously this is the same as this. We have the same terms. So in a frame that is moving and has both translational motion as well as rotational motion with respect to the ground frame, this is our general formula for acceleration, which relates the acceleration of a particle in the ground frame with respect to the acceleration of the same particle in the primed frame of reference or in the non-inertial frame of reference. This term is our Coriolis term, this is our centrifugal term. This term arises because of the rate of change of angular velocity if angular velocity is not constant, and this term is our pseudo force, which arises because of the linear acceleration of my non-inertial frame of reference. So that ends this series.